All right, so I'm going to talk about bringing the UAPI boot specification to legacy BIOS. So for that, maybe first like a show of hands, who is familiar with the UAPI boot spec? Okay, different question, who has used systemd boot? Yeah, all of you are familiar with it, you just might not know that yet, because that's what systemd boot is using for all of its boot entries. And sort of the idea is that it's a common directory with like a well-defined config format where multiple distros can just drop their boot entries and then the bootloader can pick them up from there. And sort of it comes with all the nice fancy new features, like you get automatic boot entry selection based on like the version and per OS sort key grouping. And you also get nice stuff like boot counting, so that if a new update kind of fails to boot, then it will attempt it a couple of times, fall back to the previous version. Like you get all that nice, shiny stuff with the UAPI boot spec. And sort of the way it works is it's just way simpler to use than something like, let's say, grub, and obviously more featureful than things like syslinux. So who's implementing the UAPI boot spec? I mean, predominantly, obviously, systemd boot. That's kind of where it mostly comes from, and that's only on the UEFI side. Then initially, when I planned this talk, I thought that systemd boot was the only thing implementing this. I've recently learned that actually Barebox also has optional support for this, so that's on the embedded world side, so mostly for ARM. But if we look on like the legacy BIOS side on x86, then there's not really anything implementing the UAPI boot spec till now. Now, to kind of address the elephant in the room, like why would anyone still care about legacy boot in 2025? Like that stuff should have been dead, what, 10 years, 20 years ago? Like no one should be using it anymore. If you're talking about like physical machines you use yourself, yeah, that's probably right. But in sort of the server world, I mean, there are some niche, small server providers out there that still do it, like niche providers like AWS, for example. Sure, their cloud, like their VM offerings, they all support UEFI, but if you want a metal machine from AWS, none of the x86 metal machines support UEFI yet. They're all still just legacy BIOS. So that's the one example where I've stumbled over this, but I will guess there are probably quite a lot of server providers that still don't have proper UEFI support everywhere. So the situation that you end up with then is that if you want to build a hybrid disk image that can boot both on UEFI machines and on BIOS machines, you're kind of stuck between two options. Either, I mean, you could just use grub for both sides. That works in legacy and in UEFI mode, but then you don't get any of the nice UAPI features. Or the alternative you can do is you use systemd boot on the UEFI side, you get all the nice new features there, and then you just stick something like syslinux in for compatibility. But then that leaves you with having to maintain two different sets of config files, one for the UEFI world, one for the legacy BIOS world on every system update. You then need to keep them in sync. So it kind of looks a bit like this. You would have like the shared stuff here, so the kernel, the init.rd, obviously that's shared between both worlds, but then you have the UAPI boot spec configs for systemd boot, and then you need to maintain a separate config file for syslinux, and if you make any changes, change your command line or whatever, you need to make sure that they're always manually kept in sync. So works, but not great. So that's why I tried to implement a UAPI spec compatible legacy bootloader. So the goal there is make obviously a bootloader that's compatible with the spec, works on legacy BIOS, shares the boot entries with systemd boot. What explicitly wasn't a goal in this project is any kind of UI. So that will only do the auto selection based on like the sorting defined in the spec and all that. No like custom UI selection of any boot entries, because that on legacy BIOS, bit annoying. So if we just look at like in general the difference between like how stuff works in the UEFI world versus legacy BIOS. On UEFI, you get your nice UEFI firmware that provides like on the one hand side the runtime services, so that what your operating system uses to, for example, read the UEFI variable store and those things. But on top of that, you also get the boot time services, and they provide you things like a file protocol or some text output protocol. And important, like the file protocol really gives you file system level access to individual files, so quite a high abstraction level. And then your EFI application that you write on top of this, that's running nicely in 64-bit long mode with paging enabled. You have like a well-defined binary format with some proper ABI calling conventions. So fairly nice world to develop in. If you then look on the BIOS side, you get 446 bytes of MBR code. That's in 16-bit real mode with segmented memory addressing, so that takes a bit of getting used to working with. And all the BIOS provides you are some interrupt services, which, like on the surface, if you look at the names, something like video service, disk service, sounds like that provides you a lot, but really that's very low level. So like the disk service gives you direct raw access to the disk, but not any abstraction on top, like if you want something like partition handling or any file system drivers, you're completely on your own to implement those from scratch. Nothing of that is in any way abstracted away for you. So to implement the bootloader, basically I had to implement all of those parts that you kind of get for free in EFI land on top of just those very simple BIOS services. So the way that kind of looks from an architecture perspective is obviously there's the MBR part. That's the stuff that you always get for the initial init. No way to fit an entire bootloader in those, just a bit over 400 bytes. So that mostly just has the job of loading a stage 2 loader somewhere from disk, and then that stage 2 loader is doing all the actual work there. So all the parsing the partition table, identifying where the ESP is, then parsing like the file system from the ESP, finding all the config entries, selecting the correct config, and then obviously finally executing the kernel. And stage 2 is also the part where, like in the MBR, that's all just direct assembly, and then in stage 2, at least we're finally working with C code, so it gets a bit more comfortable working with it from that point on. And more in detail, like if we look how this looks on disk, like the MBR always has to go into the very first sector on disk. Then you have like the GPT partition table after this, and after that your ESP partition. And the nice part is, if you look at like the sectors where on disk this is stored, usually your partition table is only in the first part of it, but the first partition, conventionally at least, only starts after 1 megabyte on disk. So that gets us quite a bit of free space that we can just work with without interfering with anything else. And that's also exactly what I did. So I just placed the stage 2 in that empty space. That way, it's essentially for free and not using up any space that you would have used for anything else otherwise. And then the firmware just goes in, always loads the MBR to this well-defined memory address, and then the job of the MBR is just to load the stage 2 from disk to some other memory location, execute that, and then that handles all the steps I just described before. So let's see that in action. I have a... Is that large enough? Probably not. Better? Good. So I have a very simple disk here, just with an ESP partition and a root file system. And if we just run this first in EFI mode, that is, let's just confirm that it's running on EFI now. I mean, nothing unexpected there. And if we just look in the ESP partition, there really is just the system deboot installed on there, and then just one single config in the UAPI boot spec format, no custom additional configs. If I now kill this VM and instead run it in legacy mode, it still boots. And what we see here, like it is booting just regular BIOS, nothing with EFI. Then those messages are from the custom bootloader, and then starting the kernel. And if we just confirm this, yep, nothing with EFI involved there. So it booted with exactly the same config files that the EFI mode used, just in legacy mode now. Thanks. Now, what quite a few of you are probably wondering now, what about UKIs? I mean, pretty much every other talk on this conference was in some way related to UKIs, so obviously we want to keep support for those. I mean, I think I don't need to recap what UKIs are. They were mentioned often enough. It's just single EFI executable that bundles everything you need. So if we look inside of one, they are basically just EFI executables, so PE binaries that start with some stub loader, and then that stub loader is responsible for identifying the remaining sections within that same binary, and then loading them into memory accordingly and executing them. Now, can we run those on legacy BIOS? I mean, obviously, we can't just execute an EFI binary there. That's not going to work. But at least in my opinion, like the point of a UKI isn't really that it's an EFI binary. Like it's just that it's some self-contained executable that's combining your kernel, your initRD, your command line into a single self-executable package. Whether that's an EFI binary, more an implementation detail than really the important part. So could we kind of replicate something similar to that on legacy BIOS? And what even is an executable in legacy BIOS land? Like that concept doesn't really directly exist. But what we do have are Linux BZ images. I mean, they were never designed as a general executable format, but with a bit of tweaking, you might be able to abuse them as one. So if you look at how a Linux kernel BZ image is structured, it starts with a setup header, followed by the real mode code. So that's the stuff that's executed in 16-bit real mode, and then the protected mode code that's like the actual real kernel stuff. And that setup header just defines like the size of both of the other sections there, and then some jump point to start the execution within the real mode code. And now the idea is, if instead of using those sections the way they are intended, forgot that, that's just how it's mapped in memory, then the idea is, if instead of using the sections the way they are originally intended, we replace the real mode code with a tiny PE loader stub that's able to parse a PE binary and map all the sections accordingly. And then we just place the entire UKI the way it was, where normally a kernel would expect a protected mode code. As long as the loader stub is mapping everything correctly, that gets you essentially a UKI in legacy mode. Now, that would work, but then that kind of breaks EFI support, because now on the EFI side, you have directly the PE binary. And on the legacy side, with this design at least, there would be a BZ image that's wrapping an original UKI. So, can't execute that wrapped version on EFI anymore. So can we somehow have both? And if you look into like how EFI executables, so PE binaries, are structured internally, for some arcane historic reason, they start with a DOS header before the actual PE header, where inside the DOS header, basically all fields are just 0 or completely ignored, except the very final one. And that field is just a pointer or an offset from the DOS header to where the actual real PE header starts. Now that's where it gets fun, because that's an arbitrary offset that you can control via the header. You can just shift the PE header down and inject whatever arbitrary payload you want inside there. So if you do a bit of size calculation, you see the DOS header is just 64 bytes. The setup header in a BZ image doesn't start at the start of the file, but at some offset. And luckily, those work out that you have space that both can coexist within the same file. And interestingly enough, the kernel itself is actually using this trick if you enable the config EFI stub option, where you can directly execute the kernel as an EFI binary. It's abusing exactly the same trick there. And if you then build a UKI with this trick enabled, it looks a bit like this. So it starts with the DOS header, followed by a BZ image header. I then have some initial init code, some trampoline to jump over the PE header that follows after it. Then the loader code that's responsible for like loading the PE sections in legacy mode. And then all the regular PE sections that you would have in a normal UKI. So that final part is where your normal EFI stub, your kernel, your initRD, all that stuff lives. And then this Polyglot UKI binary, you can kind of view this from two different aspects. So on the one hand side, you can view it as an UEFI binary, where from the view of an UEFI firmware, it just has some headers with code and data after it, and some random unused junk in between that it will just fully ignore. And if you view the exact same file through the lens of a BZ image, you have the setup header, then both the init code, the PE loader, and also, importantly, the PE header is just all considered part of the real mode code. So a bootloader will just map all of that into low memory, and then all the remaining sections are mapped into high memory. So that's kind of the full view there. And I also have a demo for that. So this disk here. If we run this in UEFI mode again, boots in UEFI mode, and then run it in legacy. We see again the BIOS up here mentioning, then the bootloader, the same message as before, just saying that it's now booting a UKI. And then these messages here, they are from the PE loader stub that is then responsible for loading all the sections correctly into memory. And if we look on the ESP, there really is just systemd boot on there and this UKI and nothing else on there. So a couple lessons that I learned along the way in implementing this. I mean, first, just the, let's say, joy of debugging 16-bit real mode code, because you can attach GDB to a VM running in real mode code if QEMU is running in 32-bit mode. The second you run QEMU in 64-bit mode, GDB is going to have a panic attack as soon as you try to debug real mode code. Fun. Also, in theory, GCC is mostly emitting 32-bit addressed prefix instructions when it's compiling for 16-bit mode, except for struct member access. There it doesn't. So if you use some tricks called unreal mode to get access to the full address space, you need to be really careful when you're working with structs to first copy them from high mem to low mem and only do the access then, because otherwise, yeah, everything is just going to break horribly. And one thing, like obviously testing kind of application logic, like the file system drivers, or whether the loader is parsing the config files correctly, doing that directly in real mode is just pain. So there instead I kind of developed an emulated mode where all the same application logic is compiled to a normal user space binary, linked against like an emulator binary that just mimics all the BIOS functionality, so you get the normal user space debugging experience there. And that even lets you do stuff like unit tests. Okay, so finally, just a quick summary of what the current state of the project is. The basic bootloader is functioning. It has full support for type 1 bootloader entries, so that's the config file-based ones. And it has support for the type 2 entries, so UKIs, but obviously only via this Polyglot UKI trick, not just straight up UEFI binaries. What's completely missing as of now is any support for boot counting, because there the issue is file renaming on FAT32 is a bit painful, at least if you consider cases where the length of the file name might change. So that's why I haven't gotten around to doing that part yet. And one thing that's partly working is to make those UKIs also possible to use them with kexec, because I mean, after all, they're just BZ images now, so you can theoretically kexec those. And I've gotten that to work with some custom purgatory code. I've not yet gotten that to work with the purgatory that kexec tools ships with yet. Still not sure exactly why. Also, all of this is fully implemented with GitHub action-based tests, so any Git commits are just automatically checked that all the stuff is still working. Right, with that, thanks everyone, and if you want to try it out or contribute to it, the link is here.
Porque no los dos is one of the favorite memes of my friends in Miami, so I loved seeing that in the presentation. Are there any questions before we head upstairs to the closing session? Oh, here we go.
Have you considered having your bootloader kind of parse regular UKIs instead of those polyglot UKIs?
Yes, I actually initially considered that. That would have probably been easier, but I thought sort of in order to also make the UKIs like truly universal and also work in other contexts this way, like it also gives you the ability with QEMU, you can just tell it, here's a kernel, please boot this, and that will work with the Polyglot UKIs also, whereas if just the bootloader was handling the parsing, then those stuff wouldn't work. So yeah, initially I tried to do it this way, but then I thought the polyglot way was a bit more interesting.
Yeah. Maybe you could do both?
Yeah, probably.
So in principle, this could be integrated in UEFI, so that the UEFIs would get built this way. Have you considered?
At the moment, I'm doing it with like a custom injecting script, but yeah, it could very well be integrated in UEFI. Like mostly, it's just adding some sections in there. One thing like that's a bit annoying is if I go back to the kernel header. Come on, where was this? Here. This sys field unfortunately also needs to be kept in line with the full size of all the sections. So that means like it doesn't just take like adjusting the sections within the PE binary, but also going into like this stuff in the initial header and also making that always be in line with any other changes to the PE. Because initially I thought I could just create a stub, so just take the systemd stub, always pre-inject this stuff, and then you just use this stub instead of the normal one with the existing UKIFI, and that mostly works except for you need some special magic to adjust the sys size there. But if you extend UKIFI to just adjust this one single size field, then it will work directly. Yep.
I think that Leonard hates this, but I see the appeal for other people.
Okay.
I was wondering, like you inserted your second stage bootloader into the ESP, into the white space, basically. Why didn't you turn that into a proper partition, like just to protect it or something? Like, which is, I think, what grub does.
I mean, that would have been another option, yeah. I mean, mostly I did it just to make like the MBR really simple. I always wanted to use like a hard-coded offset instead of already having to do some GPT parsing within the MBR, but yeah, like to properly use this productively, going for a partition would definitely be the safer option. Yeah.
I mean, the thing that I'm wondering about is like if you boot up a system with such an ESP, which such a GPT partition table, and then it does stuff like, for example, run systemd repart to add a couple of partitions or something. Will this be destroyed or?
I tried that, and it looks like repart also keeps this convention that the first partition always only starts after 1 megabyte, and pretty much all tools I use keep this convention unless you explicitly tell them don't do that. So like you need to explicitly tell pretty much all formatting tools, yeah, actually create a partition before this 1 megabyte offset. So unless you actively do something to break this, it will work. But yeah, partition would probably be the safer option.
But what about the other data that's in the various headers up top? They are not risk, like there's no risk that they get corrupted by fdisk or something?
Which headers do you mean?
Like the MBR stuff and your...
sorry.
Like...
I mean, the MBR is always ignored by GPT anyways. Like GPT tables by definition start on the sector after, because for like compatibility reasons, and usually have like a protective MBR that just prints some message of, hey, you can't boot that. So most tools, as long as some MBR stuff is there, will ignore it and will only write the protective one if it's not there. But yeah, obviously some tools might do weird stuff with that.
Any further questions before we head upstairs to wrap? Well, thank you for your talk, Nicholas. And I encourage you to, well, definitely a round of applause.
Thanks.